Okay, so in this video, we are going to prove the converse of the result in our previous video. If you recall, the previous video said that if you have a quadrilateral where the diagonals bisected each other, automatically the quadrilateral was a parallelogram. And here we are flipping the assumption with the conclusion. So here's the result we're going to try and prove. Show that the diagonals of a parallelogram ABCD. So here we assume we have a parallelogram, and we will show that the diagonals of a parallelogram must bisect each other. So it's the converse. And therefore the conclusion from this video and the other one is that a quadrilateral can only be a parallelogram if and only if its diagonals bisect each other. So as always, we can draw a picture, but now we can actually explicitly draw a parallelogram because we are assuming that the quadrilateral ABCD is indeed a parallelogram. And as always, label the vertices counterclockwise. So we'll start here with A, B, C, D. And let's write first what we know. And what we know is quite simply that the quadrilateral ABCD is a parallelogram. Well, we want to capture this statement using an equality between vectors. Well, again, opposite sides must be of the same length and parallel. Therefore, if we view the opposite sides as vectors, they have to be equal, because vectors are equal if and only if they have the same length and they have the same direction, therefore are parallel. So the vector AB must equal vector DC, and vector BC must equal vector AD. And what do we want to show? Well, the result says show that the diagonals of what you know to be a parallelogram will bisect each other. So let's draw both diagonals, diagonal AC and diagonal BD, and we want to show that they bisect each other. Well, let's give a name to the point of intersection of both diagonals. Naturally, we can call this E. Well, they will bisect each other if they cut each other in half. So, in terms of vector equalities, that would mean that E is the midpoint of AC. Therefore, the vector AE equals vector EC. And E is also the midpoint, and that's what we want to show, of segment BD. Therefore, vector BE would have to equal vector ED. And you could also say in both cases, if you look at the diagonal AC, if AE equals EC, then automatically they're both equal to 1/2 of AC. And the same thing for diagonal BD. If vector BE equals vector ED, then they're both equal to 1/2 of vector BD. And you can prove either in each case this equality or this one, and automatically the other equality will be true. So as long as you prove either this one or this one in both cases, then you'll have the result that the diagonals bisect each other. Well, now that we have clearly our assumptions, what we want to show, let's start our solution. As you will see, the solution is remarkably simple, but at the same time, it's a bit subtle. It won't be as direct as the previous solution. So let's start with vector AB. Again, we are trying to involve the vectors on the diagonals of our parallelogram. So as before, we'll start with saying, well, vector AB is the same as vector AE plus EB. Well, now what is the assumption? That vector AB equals vector DC. So let's consider now vector DC. Vector DC can be obtained by doing vector DE plus vector EC. And now we have here 4 vectors on the diagonals, right? Vector AE, vector EC, vector EB, and vector DE. The idea is, how can we combine them together? Well, by assumption, vector AB and vector DC are equal because we assume that we had a parallelogram. So both of these are equal as vectors. So let's equate them and see what we can do from that point on. So vector AE plus EB is equal to vector DE plus EC. Now the question is, where do we go from here? Well, if you're ever unsure of how to proceed next, go back to what it is that you want to show. We want to show that AE equals EC and BE equals ED. Well, if you think of it this way, what we're saying is that the vectors AE and EC go together, but as you can see, AE is on the left of the equality, EC is on the right of the equality. And similarly, we want that BE equals vector ED, so these two vectors go together. Well, vector, BEEB, close enough, is on the left, and vector ED or DE is on the right. The idea is, let's put the two vectors that belong together. So we'll keep AE on the left, and AE goes with EC. So we are going to subtract EC from both sides. So if we send EC on the left-hand side, it will become AE minus EC. And that will be equal to, well, vector DE, we're leaving it here. And now we're going to send, because think of it as, well, either BE equals ED, or this is the same statement as if you reverse both vectors, the same as saying that EB equals DE. Right? This will prove the same thing. If you go back to your picture, vector EB is the vector pointing this way. Vector DE points in the same direction. So if both of these are equal, of course, E will be the midpoint of segment BD. So we'll go with that instead of this equality. So now we will send EB onto the right-hand side. And of course, we'll have DE minus EB. And now the question is, well, where do we go from there? We've combined on the left-hand side the vector AE minus EC, and both of these go together. And we've combined on the right-hand side vector DE with vector EB, which also go together. The question is, where do we go from there? And this is where the result is a little subtle. We have here an equality between two vectors. The vector right here equals the vector right here. And remember that vectors are equal if and only if they have the same length, and in our case, more importantly, they have the same direction. So look at vector AE and EC. Right? We don't know anything about these two vectors in our assumptions, But from the picture we know something. Look at the diagonal AC. We know that vector AE lies on the diagonal, and vector EC also lies on the same diagonal. So if you add two vectors that are parallel to each other, like we don't know, or subtract, we don't know the length of AE with respect to the length of EC, but since they lie on the same segment, they're parallel. So if we add or subtract vectors that are parallel, the result will also be parallel, therefore pointing in this direction, or maybe in this direction. But what we know is that vector AE minus EC is parallel to vector AC. So let's write that down. So from the picture, vector AE minus vector EC, since both vectors are lying on the diagonal AC, if we add or subtract parallel vectors, the result is also going to be parallel. So AE minus EC, and we write parallel usually with slanted bars. So this means that vector AE minus EC is parallel to AC. So it has either the same direction as AC or the opposite direction. But in either case, it will either be pointing this way or this way. So the vector will either point like this or maybe like this. Let's consider now DE minus EB. Well, vector DE and vector EB both lie on the diagonal DB. And if you add or subtract vectors that are parallel, the result has to be parallel, therefore in the same direction as DB or in the opposite direction. So the same can be said about DE minus EB. DE minus EB must be parallel to the other diagonal, DB or BD or DB, doesn't matter. Let's go with DB. Because if we add or subtract parallel vectors, the result is still parallel. And look at the direction of DB. When we subtract from DE vector EB, the resulting vector will also be on the diagonal, DB, so it will be either pointing down this way or up this way. So they'll have to be parallel to a vector that looks like this, or it looks like this. But now think of it. The vector AE minus EC is pointing this way or this way, and the vector DE minus EB is pointing this way or this way. But both vectors are equal, and yet they clearly cannot have the same direction. And so what we have now looks like we have a contradiction. How can two vectors be equal if they have clearly opposite direction? Not opposite, but different direction. Well, the only way is for these vectors to have no direction. Right? If this vector has direction, this one has the same direction, but clearly this is impossible because vector AE minus EC will have this direction, or the opposite, and vector DE minus EB will have this direction, or the opposite. So clearly, in both cases, we don't have the same direction. So if these vectors have a direction, we have a contradiction. But we know this equality is true. So both vectors cannot have direction. And what is the only vector that doesn't have direction? That is the zero vector. So the only way out of this apparent contradiction is if both vectors don't have direction, therefore they are both equal to the zero vector. And now we no longer have a problem. And now think of it. What we have from this is vector AE minus EC equals the zero vector. And vector DE minus EB equals the zero vector. Well, send EC on this side, send EB on this side, and what do we have? Vector AE equals vector EC. And vector DB equals vector DE, equals vector EB. And what did we want to show? That vector AE was equal to vector EC. Check. And that vector EB was equal to vector DE. Well, vector EB equals vector DE. And now we're done. So indeed, if you have a parallelogram, the diagonals must be bisecting each other. So this line segment AE equals the line segment in terms of length, EC, and the length of BE is the same as the length of DE. And the only tricky part of the argument here was that because this vector was lying on the diagonal AC, and this vector was lying on the diagonal DB, both vectors had to have different directions, therefore could not be equal unless both vectors had no direction to begin with, therefore were equal to the 0 vector. This was kind of a subtle argument, but you'll see in some cases, and other examples on the problem sheet, you will encounter problems like this. If you try to prove that AE equals AC independently of BE equaling ED, you'll never be able to prove this. You have to prove both equalities simultaneously within the same equation. And usually when you get to a point like this, that's when you'll use the argument of you have an equality of two vectors, but they can't possibly have the same direction. Therefore, the only way out of this contradiction, or at least apparent contradiction, is both vectors must be the 0 vector. So you'll use this trick again on other problems.